It is a pleasure to welcome you to the third edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Biogeotechnics was hosted in 2022 during the third edition of the AGERP lecture series. The following lecture on Phytoremediation, a sustainable technique to ameliorate polluted soils, was delivered by Associate Professor Oznur Karaca at this workshop. Dr. Oznur Karaca is an Associate Professor of Geological Engineering at the Canakkale Onsekiz Mart University. Dr. Karaca received her PhD in Geological Engineering Department from Suleiman Demirel University. She has been at the University of Illinois at Chicago in the Department of Civil and Materials Engineering for 1 year as a visiting professor. Her research areas include engineering geology, geotechnical and geoenvironmental engineering, remediation of contaminated soils, sediments and mine wastes, GIS and remote sensing. She has published 18 journal papers, 1 book chapter, and 44 conference papers.
Hello everyone. Thank you for the kind introduction, and I would like to thank the organizing committee for this well-taught workshop. Also, I would like to thank for the invitation and giving us an opportunity to be here with you and share our experiences. So my presentation is about phytoremediation, a sustainable technique to ameliorate polluted soils. In this concept, I'm going to talk about the problems related with the polluted soils in general, and then problems with mining sites in detail actually, and then I will give some sample studies from Turkey, remediation possibilities, phytoremediation, and also I'm going to talk about the problems with saline soil. Soil pollution is defined as the accumulation in soils of persistent toxic compounds, chemicals, salts, radioactive materials, or disease-causing agents, which have adverse effects on living things. There are many different ways that soil can become polluted, such as seepage from landfill, discharge of industrial waste, percolation of contaminated water, rupture of underground storage tanks, or excess application of pesticides, herbicides, or fertilizers. The most common chemicals involved in causing soil pollution are petroleum hydrocarbons, heavy metals, and also pesticides. I will do like this. When we say heavy metal, means elements having a density greater than 5 in their elemental form. Maybe these are essential for us in trace amounts, but they become toxic at high concentrations. There are many different kinds of sources, but the most important sources of contamination in soils are those connected with human activities, such as metal mining, smelting, industrial activities, waste disposal, using agrochemicals, and manure containing veterinary drugs. In terms of budget, the management of contaminated sites is estimated to cost around 6 billion euros annually. Mining is the extraction of minerals and other geological materials of economic value from deposits on the earth. Mining industries provide us the materials to build infrastructures and instruments of daily use, such as obtaining large amounts of energy. So we need them. But the problem is improper mining activities and after. The first effect of mining in the environment is deforestation and destruction of the habitats of many species when plants, trees, and topsoils are cleared. Environmental impacts of mining are mine waste, source of heavy metals, and maybe the most important problem related to the mining sites is acid mine drainage. They affect the biodiversity, amenity, and economic wealth. So defining the expected metal concentrations in leaching effluent is more important than the actual total heavy metal concentrations. To determine the pH, grain size, mineralogy, chemical composition, heavy metal speciation also are important. Otherwise, they cause unacceptable risk to natural life and human health. Environmental impacts are mostly influenced by geological factors. Lithology and rock alteration are the source of contamination. Natural rocks include minerals. When we excavate them, rocks break into small pieces, and some minerals can have a detrimental effect when exposed to air, and we will talk about this in detail. Topography and hydrology are the other effects spreading the contaminants, because drainage systems can transport polluting materials to other basins. Mining and milling methods are also important. For example, open mining activities have much more detrimental effects. If you look at the problems of mining and mine tailing disposal sites, in the nature, coal is here, and to reach the coal, we must excavate all these layers, and problems start here. Related to this excavation, we lose forests and we encounter with different pollution due to mining. Noise is a problem. Also, they affect the water quality, soil quality, and another issues are dust, dam safety, also soil erosion, of course, the heavy metal pollution and acid mine drainage. We will focus on them. We said that mining activities cause huge damage to the landscape, and also the mines affect the water, and due to the low quality of water, fish and other living things die. This is an aerial view of from Ohio River. The wastewater of mining comes to the river and contaminate there. And I said that maybe the most important problem related to the mining sites and mining activities is the acid mine drainage. It is polluted water discharged from abandoned mines. Metal sulfides, when exposed to air and water, react to form a sulfuric acid solution containing dissolved metals. And this phenomenon is connected with the biooxidation of pyrite or other sulfide minerals. This photo is from an abandoned mining site in Canakkale, mine city, and it's not a natural lake actually. After the abandoned mine, precipitation, which falls into the open pits, is exposed to sulfide mineralization in the pits and forms acid mine drainage. Acid mine drainage or acid rock drainage both produce acidic waters. And here we see the formation mechanism of acid mine drainage. If we say simply, when we have sulfide mineral, water and air, the result is low pH and metals, and it's called yellow boy. And it is an example to yellow boy. from Canakkale, again from my city. And here the pH of AMD can be less than 3. Acid mine drainage solubilizes and mobilizes some heavy metals, and streams are often devoid of life. If you look at the problems with mining sites in Turkey, this one is the biggest mining area in Canakkale. Maybe you can see the trucks here, and we can understand how big it is. And our problems are the mine waste, tailings, acidic lakes, and other issues are the soil and water erosion. Also had problem because people use the water for the irrigation. Okay, it doesn't look like the acidic as I showed in previous slides. It's not red, but we don't know the quality of the water. Another problem is dust and air pollution. Coal is burning when exposed to oxygen, and also big scars. In Turkey, there are different kinds of mining activities. These are open or underground mining for various types of ores, such as lead, zinc, gold, copper, or coal minings. In general, in my city, coal minings and gold also are very common. Generally, companies are coming to the site and take the mine and then abandon the area. And the results we have are the mine waste, mine lakes, and different kinds of pollution, of course, lots of risks. So what should we do? We need to define, we need to study much more deeply and define clearly the geochemical interactions at tailing sites and wastewater courses and their effects on agriculture. To protect the environment, the key point is prevention and remediation. Of course, prevention is what we relevant here because remediation is more expensive and time consuming than the prevention. But there are different kinds of remediation technologies, such as soil washing and soil flushing, stabilization and solidification, vitrification, electrokinetic remediation, and phytotechnologies. I will give two sample studies from Turkey. We did these studies with Professor Krishna Reddy from UIC in USA and Professor Claudio Camaseye from Vigo University in Spain and Professor Mustafa Bozcu from Canakkale Onsekiz Mart University in Turkey. In these projects, our study objectives were to investigate the characteristics of the mine sites. For this purpose, first we determined the physical and chemical characteristics of the mine tailings and also lake sediments, and we defined the heavy metal content. To determine the environmental impacts of the materials, we did some leachability tests. And for the remediation options, as I said in previous slides, there are various remediation options, but most of them are expensive and maybe more harmful because they use chemicals to remediate their to environment. Among those remediation options, we investigated the capability of electrokinetic remediation in the removal of heavy metals from mine tailings and lake sediments, and also we investigated the phytocapping or phytoremediation. Our study area is located in the northwestern part of Turkey in Biga Peninsula in Canakkale. Maybe most of you know here as Troya. This one is our first project area. These are the abundant mining sites, and these are the acidic lakes in the region. We collected the samples from 5 of them. This basin has lignite beds having important economical reserve, and lignite deposits have high sulfur, and they are rich with inorganic materials such as arsenic. We collected the samples from the rock, tailings, and also underlying sediments. Then, before starting the remediation tests experiments, we characterized the materials, and also we determined the metal contaminations. For the chemical properties, we defined the organic content, pH, ORP, and electrical conductivity. To understand the environmental impact of the materials, heavy metals, we did some leachability tests. For this purpose, we performed the batch experiment and also column experiment. For the column experiment, we used a small column, and during the experiment, we used DI water, and we collected the sample effluent here. Then we analyzed them. And we found that the soils and lakes have low pH and high electrical conductivity. Also, the materials, tailings, rocks, and underlying sediments have a higher concentration of lead, chromium, nickel, barium, and arsenic. And we saw that leachability of sediments and tailings is more than the rocks. Iron content in soils is very high, and it comes from pyrite. At the end of this study, we understood that the material have relatively high amounts of leachable heavy metals, and the environmental risk associated with the leachable heavy metals and potential method to remediate need to be further investigated. And our second project area is here, and here is old mining area and the acidic lake, and here is the new mining area. When we take the cross section from north to south, we have this, and coal is here. As I said before, to take the coal, they excavate all these layers and put the waste tailings here. Then after they finish their job, they abandon the site, and after the precipitation, we have acidic lake here, and this one is new, and maybe later it will be like this. In this project also, again, we characterize the sediments and tailings. Again, we have high acidic conditions, and the materials electrical conductivity value were high, and we have lead, iron, arsenic, barium, and aluminum with high concentrations. Again, to understand the environmental impacts of the metals, we did the leachability and bioavailability test. But in this project, in addition to column experiment, we also did TCLP, SPLP, and sequential extraction analysis. After the column experiments, we saw that the mine tailing released much more metals than the sediments, and iron was easier to release from the mine tailings than lead, but similar concentration was found for lead and iron in sediment. At the end of the TCIP and SBIP, we saw that iron leached at higher concentration than lead, but this is because of the much higher concentration of iron than of lead, but the fraction of lead extracted is much more important than the iron. The extraction of lead is similar for both mine tailings and lake sediments, but the TCIP method tends to extract higher concentration than the SBIP. As a result of the tests, we understood that both samples are considered hazardous for the environment. To understand the fractionations of the metals, we did sequential extraction analysis. As we see here, lead is evenly distributed in 4 fractions, whereas iron was mainly concentrated in fractions 3 and 4. The environmental risk of the mine tailings and lake sediments in Canakkale mainly due to 2 factors, and one is continuous release of heavy metals and the acidic conditions. In these conditions, wildlife is not sustainable in lakes or soil. Here we see the abundant mining sites and residential area. It's very close to residential area. This distance is 200 meters. If you look at the remediation possibilities, when dealing with large contaminated areas like Canakkale, conventional methods are impractical and economically unfeasible. For these projects, we applied 2 treatment methods. One is electrokinetic remediation technique, and other is phytoremediation or phytocapping. Here, I will focus on phytoremediation. Phytoremediation is an energy-efficient and eco-friendly technology to ameliorate soil, surface water, and groundwater or other contaminated media. This technology can be used to clean or stabilize organic and inorganic contaminants. Phytocapping is cost-effective, low maintenance, environmentally friendly, and it reduces wind and water erosion. It prevents the contact and oxidation of the solid materials with the atmospheric oxygen. If you remember, I said that our main problem are these. We have pyrite in the study area and the iron concentration is very high. So oxidation and acid mine drainage are the big problems for us. If you look at the phytoremediation mechanism, there are a number of phytoremediation strategies. Phytostabilization is using plants to reduce heavy metal bioavailability in soil. It stabilizes the contaminants near the root area. Phytofiltration is using hydroponically cultured plants to absorb heavy metals from groundwater or aqueous waste. Phytodegradation, rhizodegradation, or phytovolatilization are used for organic pollutants. Phyto extraction is using plants to extract and remove heavy metals from the soil. If you remember our soil properties, we have high acidic conditions, and the materials have high electrical conductivity values and high concentration of metals. In these conditions, of course, it was difficult to grow plants. We chose for the plants. We chose for these projects two plants. We chose one is oat plant and another is sunflower. First, we sowed the seeds, but because the soil is too acidic, 1 week after the germination, they all died. Then first we try to add biochar to increase the pH of the soil because pH was about 9. Biochar's pH was 9, but it didn't change the pH value of the soil. Then we added lime to the soil. Lime increased the pH. To see the effect of biochar and lime, we prepare the pots with only soil and lime, and also soil, lime, and biochar. And during the experiment, we used growth lamps. We don't see here actually to maintain daylight period of 16 hours per day. The lamps were hung about 30 centimeters above the plants. In these conditions, plants were germinated and survived. For 3 months, we measured the number of growing plants, height, and number of the leaves regularly. After the experiments, we determined the germination ratio. The addition of 5% of lime had a significant effect on the pH, and this allowed for the germination of plants that resulted 67% germination for oat plant and 17% for sunflower. The combination of the two amendments, lime and biochar, enhanced the germination ratio up to 97% for oat plant and 47% for sunflower. Also, we calculated the survival ratio. Plants were not able to grow in unamended soil and biochar amended soil. These are here, and we cannot see these in the graph. However, the survival ratios in the test with lime and biochar were very high for oat plant. It's 90 and 100%. Sunflower survival was 100% only in the test with lime and 5% biochar, and with only lime, the survival was only 20% for sunflower. The remediation results we obtained from these studies, I hope, should be used in the design of practical and sustainable remediation processes. And here, I will give 2 success stories from the world. One is from Turkey. This is from gold mining area. Here is not actually real hill, a natural hill. This is mine waste, mine tailings, and after they finish the operation, they planted olive trees here and succeeded. and another is from England. While mining activities were continuing, extra land close to the mine was transformed into a large public park. As I said at the beginning of the presentation, mining activities are not a unique problem for soil pollution. Here I will give a short example from our studies about saline soils. Soils with soluble salts that restricts plant growth in the plant root zone are known as saline soil. Causes of salinity causes of salinity are excessive or incorrect use of fertilizers, water, pesticides, or excessive water withdrawals from areas close to the sea. And sources of salinity, mainly oceans, main material, topography and climate, and also anthropogenic effects. The climatic changes that have occurred with the deterioration of the natural balance have led to an increase in dry periods. This global change affects all living things negatively. It triggers drought and salinity problems in agriculture areas. Salinity soils affect the environmental biodiversity as well as civil engineering facilities. At high pH, calcium precipitates as calcium carbonate. Zinc and iron deficiencies are very common in these soils, and sometimes manganese and copper deficiencies are seen, and boron toxicity also is common. If you look at the remediation technologies for the saline soil, we have improving drainage, leaching, reducing evaporation, applying chemical treatments, soil washing, phytotechnologies, and electrokinetic remediation techniques. But based on the previous studies, the conventional techniques are inadequate, expensive, and mostly ineffective. For the saline soil, we did several studies in Canakkale, but this one aimed to understand the effect of usability of various electrodes to remove salinity from the saline soil during the electrokinetic process. Actually, our subject is phytoremediation. Just I wanted to show you this result because it's interesting. Actually, we expected this, but first we did sampling from the site, then we characterized the materials, and then we did electrokinetic tests to remove the salinity. Again, our study area is Canakkale, and the soil was alkaline and electrical conductivity is high, and the soil class is low plasticity clay, and we determined also calcium, potassium, and sodium concentrations. We did several tests using four different kinds of electrodes. And these are copper electrode, galvanized steel electrode, and aluminum plates. After them, for our main project, we used graphite electrode also. But in this project, we used these. Actually, we had good results for the removal of salinity, of course, but it caused corrosion on electrodes, and half of them corrode, and maybe this contaminate the soil. So we should use corrosion-resistant electrodes. Actually, other project we used graphite electrodes, But in those projects, our system was different. First time we tried this one because we wanted to apply this system to the field. Because of that, we use this container for the test, and even graphite electrode was corrosed. So maybe other kinds of like titanium or gold should be chosen. Or applying the phytoremediation method could be more suitable for these areas. Here there is an example for saline soil. They resulted that the perennial pastures are particularly important in salinity affected areas. In conclusions, I gave some sample studies on mine sites and saline soils. For all studies, we characterized the materials before the treatment, and we investigated the environmental impacts, and then we tested, we did the remediation experiments. In mining sites, due to the mining activities, nature had been damaged in broad areas, and these areas generally become barren. The environmental effects of mines are not only because of the heavy metal contamination, also wind and water erosion and slope stability are the problems. And our main problem is acidic conditions, and these acidic conditions allow the release of metal. As a result of these negative effects, the amelioration of these areas is unavoidable. In this situation, among many remediation methods when dealing with large contaminated areas, phytocapping and electrokinetic remediation come to fore. And salinity is the other problem for the soil pollution, especially for saline soil. We learned from the study we did electrokinetic remediation is good to remove the salinity, but corrosion-resistant electrodes should be used, but these are not cost-effective. For all the studies, maybe the most appropriate method is phytoremediation. However, soil quality in mining sites should be amended first. For this study, the combined use of 5% biochar and 5% lime as amendments in the mine tailings generated the appropriate conditions for the development of a vegetative cover. Thank you.